Welcome back, everyone, to the fourth episode of Euclidean Geometry. As you know, we are doing lengths and areas, and this is the third part of that series, and for now, the last part as well. And we'll be coming back to this topic, like the problems in these topics, once we are done with techniques like exploiting complex numbers in order to solve geometry problems. And today, we are going to discuss some really cool, really amazing techniques and tools that you'll be using not only to find lengths and areas, but also like throughout whole geometry. So in all sort of problems, these are going to be really powerful tools. Now, before I begin today's session, let me tell you this is going to be like less about my explanations and more about your visualization. This session specifically, I'm talking about. So it depends more on how well you're able to perceive, how well you're able to visualize the concepts that I'll be telling you, the problems and stuff. So, yeah, and let me assure you, this is going to be one of the most beautiful sessions on geometry you'll ever attend. So, the first thing that we're going to discuss today is the carpet's lemma. The carpet's lemma. So, what is this? I basically want you to imagine a room that is full of carpets. There's this room, and it's full of carpets, such that there's absolutely no overlap. The room is completely covered with the carpets, but there is no overlap. What's the mathematical way of saying that? The sum of the areas of the carpets is equal to the area of the room. Alright, so there's no overlap, there's no empty space, nothing, and the room is completely covered. The lemma says that if I move a certain carpet, even if you think of it like naturally, ignore this. It doesn't take a lot of brains to understand that if you move a certain carpet, there would be some sort of overlapping, right? And there would be some empty area left as well if I move any of the carpets. The lemma basically says that the overlapping area would be equal to the empty ones. So for better understanding, you may look at this diagram. We have this big room, and we have taken two carpets. I moved this one, and as you can see, this is the overlapping area. The lemma says that this area is equals to the sum of these three empty areas. Alright, so I have formalized this, the formal statement for this. Here you can read it. So we have to consider some shape, some subshape, yes, some shape, which can be curvilinear as well. It's not necessary for it to be a polygon. It can be this as well. And yes, it's completely covered by n carpets or subshapes, such that the sum of the areas of each is same as the area of the room. Then upon moving a carpet, the overlapping area is equals to the empty ones. So the lemma is extremely trivial, even though there's absolutely no need for a proof. But in the live class, we have some curious students, so they were not ready to believe this, so they wanted proofs. I have formalized a proof for this, a rigorous proof, which you'll get in the notes. Okay, you'll be getting this in the notes. So yeah, very soon you'll get the notes for these lectures as well. So this is the condition that you need to focus on. When you're approaching a problem through the carpet's lemma, the first thing, the foremost thing, and the most important one is choosing the carpets. Choosing the carpets. Well, the problem would not say like apply the carpet's lemma. This is not something like that. You'll be given an absolute mess of a diagram, something of this sort. Yes? And you'll have to decide what are the carpets, what carpets should I choose as per what I'm supposed to prove in the problem. While choosing the carpets, the core thing that should be in focus is that the carpets you choose, sum of their areas is equals to the area of the room. If this condition is not being followed, those are not the carpets. Whatever you have chosen are not the carpets. Now this may seem something very easy, but people like make a lot of mistakes while doing this. I'll show you. So let me first show you a problem. So here's this problem. We've got this diagram, and we're supposed to prove that AMP, this thing, this and this, the sum of these three equals to this one. Now, if you try to solve this using the conventional methods that we have done till now, using ratio and stuff, or maybe lotus ratio lemma, similarity, and all that. Lotus ratio comes from similarity, if you remember the proof for this. So if you try to do all that, it's solvable, of course, but it's going to be like very difficult to do. Let me actually, okay, let me first do this using, let me show you how powerful the carpets lemma tool is. So looking at this statement that I'm supposed to prove, just by intuition, I think this is going to be what, the the overlapping area, the overlapped area of the carpets. Yes, and these three should be what, the empty areas. I don't know anything, I'm just going by intuition. So dpqr, this is the overlapping area. What else can I conclude from here? Whatever carpets I choose, I'll choose in a while, whatever carpets I choose, they overlap, and this is the only area that is getting overlapped between them. This is the only area that is common to them. Yes, so the carpets that I'm choosing, you may want to pause the video and try it yourself at first, choosing the carpets. So the carpets that I'm choosing, they're triangle MDC, this triangle, and triangle NDA. So let me just write it here, triangle MDC and triangle MDA. Okay, sweet. So let me first check the condition, verify the condition. The sum of the areas of these two should be what? Equal to the area of the room. The square is the room. So for MDC, for triangle MDC, this is the height and this is going to be the base. So the base is the side of the square and the height is also equal to one of the sides of the square. This is called the side A, so it's a square by 2, and same goes for this as well. So that's sum is going to be a square, which is good, right? So yes, these are the carpets. What essentially we are trying to say that earlier there was this room, it was somehow covered with these two carpets. We don't know how. We moved it in a certain way, we changed the orientation, and now we have got some overlapping area and some empty areas. And we are done. If you see, let me just highlight these carpets. So these are the two carpets that we chose. This one and triangle MDC. What's left? This is the overlap, and these are the empty areas that are left. That is what we are supposed to prove. There's nothing to write anymore. First, you have to demonstrate that these are the two carpets that I'm choosing. These were completely covering the room earlier. Yes, why? Because the sum of their areas is equals to the area of the room. We moved it, we changed their orientation, we have got some overlapping area. And since the overlapping area should be equal to, the area should be conserved, right? It should be preserved. So there we have the proof. Now let me show you the conventional method, the actual proof. Not the actual proof like whatever's given through the conventional stuff. Yes, there you are. So they're using similarity. They're making triangles similar. They're like finding ratios and stuff, and then they arrive at a certain result. They manually do this. All right. So you may want to try that as well. You can pause the video and read that proof. It's a good proof, but this one is like really easy, very powerful. All right. So I was talking about mistakes. This was a problem given to me by one of my live students, who's a very good student, and he said that this is a clear case of carpet's lemma. The problem asks, which area is greater, the pink one or the purple one? Or the pink one? That's what the problem is asking. So for a moment even I was like, yes, it is. But of course it's not. Like, we're considering the pink square to be the room, and we are saying that it was completely covered by a single carpet. That is what we are assuming when we say that this is a clear case of carpet's lemma. And we moved this one, it became something like this. And then we are saying these are the empty areas. It should be equal. So yeah, we are uncovering the whole thing. So that's how we are concluding our answer. But this is wrong. Because we have to satisfy that condition. The carpet's area should be equal to the area of the room. In this case, it's not. You see, the side of this square, the purple square, side of the purple square is bigger than the side of the pink square. Why? Look at this triangle. If you notice this triangle, it's a right angle triangle. The side of the pink square is acting as a perpendicular, and of the purple square is acting as a hypotenuse. So the area of the carpet is bigger than the area of the room. That's not possible. So this is not a case of the carpet's lemma. This is why you need to first demonstrate this condition. In every such problem, you're approaching through the carpet's lemma. So I hope that's clear. So if you want to solve this problem, it's a good one. You'll have to manually do this through like some manipulations and stuff. Anyways, so the second thing that we're going to do today is symmetry. Symmetry. Now this is one of the most powerful tools that you'll be using. It makes problems very easy. It almost feels like magic. All right. So in problems based on symmetry, the first thing, in some of the problems which are like easier, you'll be easily able to spot symmetry. So first of all, you're supposed to spot that. All right, find symmetry basically. Second, if you cannot, like force symmetry if it's possible. All right, force symmetry if it's possible. It's not like in every problem you're gonna like, yes, now let's force symmetry. No. In some of the problems where your intuition tells like symmetry may be applicable, then you do this. Once you've got symmetry, the third thing is to exploit it. This is the stuff that we're going to do with symmetry. Now symmetry also leads to techniques like transformation, which further uses trigonometry, complex numbers and stuff, especially the Euler's form of complex numbers. We'll be doing all this. You don't need to worry about that. I'm just telling you. So symmetry. Let me just demonstrate it real quick. So how useful can it be? So this is a problem. This is not really a problem. It's basically a demonstration. So it's very easy if you try to do it analytically, like the way we do it. We're provided with two squares and a circle. We're supposed to find the ratio of the areas of these two squares. The observation in the conventional methods that we use, the observation that we make is the diagonal of the smaller square equals to the side of the bigger one, right? This is the diagonal of the smaller square, which is also acting as the diameter of the circle. This is also the diameter of the same circle, which is equal to the side of the bigger square, right? So if I say the side of the smaller square, like consider it to be A, the area is going to be A square. This also means its diagonal is going to be under root 2A, which is what? The side of the bigger square. So the area of the bigger square is going to be 2A square, and the ratio is 1:2. Sweet. Now, how do we use symmetry? Like the diagram is completely symmetrical. It's not, you don't have to force symmetry here. It's symmetrical, right? So we can think of using symmetry. Now, whenever you are using symmetry, the first thing that you need to focus on, you can change the orientation and stuff. Can be changed. But you'll have to be careful while doing that. You'll have to preserve the lengths and the areas. What I mean by that? You see, I changed the orientation of the square, rotated it by 45 degrees. It still remains the square, right? Like the area of that square will still remain the same. Yes? The lengths are not going to get changed. The answer is not going to get changed. So the ratio will also stay the same, right? Now we have a very interesting thing. We've got 4 small squares, right? And these are acting as the diagonals. We have these triangles. So this triangle is half of the area of the square. This triangle is also half of the area of the second square. Same for this and same for this. If I add these four triangles, it's going to be half of the sum of the 4 squares. The 4 triangles are making up the small square, and the 4 squares are making up the big square, and that's it. We have the answer. So this is how helpful symmetry can be. Like, this was a very easy problem, of course. I was just trying to demonstrate how do we use this. And this thing, you need to focus, you need to remember while using symmetry. Now, coming to a better problem. Yes. So we are provided with a cabin. Okay, there's this cabin which is 2 miles due north of a stream from that runs east to west. So we have a stream that runs east to west, and this is, let's say, my cabin, which is 2 miles north of me, of the stream. So this is me, and my grandmother's cabin is located 12 miles west and 1 miles north of my cabin. So 1 miles north would be this, and 12 miles west. So let's say here, this is grandma. So every day you go from your cabin to grandma's cabin, which first visit the stream to get fresh. Okay, I don't care about the fresh water. Okay, what is the length of the route with the minimum distance? So I have to visit the stream as well, and then go to my grandma. All right. So from here, I'll go there. This is the stream, and then to grandma. Now it doesn't take a lot of stuff to understand that there are multiple ways to do this. I can go from here to here, right? I can choose this as well. We're supposed to find the minimum one. Which route? There are multiple routes, as you can see. Which one will have the minimum distance? So this is essentially a calculus problem where we assume the distance from me to the stream will be x, and from the stream to grandma is y. We differentiate and stuff, we find the minima and then get the answer. But the most basic principle that we can use here is the minimum distance between 2 points is what? The straight line between them. Now, the path is not straight, of course. I cannot draw this, right? I have to go to the stream. So I'll think of symmetry. Also, one more hint for symmetry here. As the book said, from where I've taken this problem, I have this divider. Think of this sort, this stream. So whenever you have something of this sort, this is begging you to like reflect across this line, this stream. So I'm going to do that. So here you have the diagram. I've reflected myself. This y is my position. So I've reflected the whole thing, the whole situation across the stream. All right. This is 2 miles, as you know. This whole thing is 3 miles, and this is 12. Right. Now, this path, if you see, let me just say that this is the shortest path. Yes. And I've reflected this. So this will be equal to this length as well. These two lengths are going to be equal, right? So instead of finding this and then adding them, I can simply find this. It's the same thing, right? So this length is x, this is y, this is also y. I'll be finding x plus y. Same for this as well, x plus y. Now, let me just erase the mess. All right. So focus on this. I have to find this. Focus on this triangle. This whole thing, this distance is 2. This distance is going to be 3. Why? I'm drawing it from grandma, right? So this whole thing is 5. And this is 12. This I have to find. It's a right angle triangle. This is going to be what? 13. So that's the answer to this problem. So instead of using differentiation and stuff, we've got the answer very easily. So this is how you exploit symmetry. Yes. Now coming to one more problem, which is more of a physics problem, but it may appear like it was provided in a maths book. So yeah. So let's just solve this. We're provided with 4 bugs, which are situated at each vertex of a unit square. Now, suddenly, each bug begins to chase its counterclockwise neighbor. If the bug travels at 1 unit per minute, how long will it take for the 4 bugs to crash into one another? So I have a square, and I've got 4 bugs. Let's say A, B, C, and D. Counterclockwise direction is the opposite of clockwise, so basically this direction, right? So A is chasing B, B is chasing C, C is chasing D, and D is chasing A. Sweet. So the orientation is going to be something like this, right? Yes. So C is chasing this one. So try to visualize this, as I said in the beginning. All four of them are traveling with a constant speed. It's a square, equal sides, everything equal. The paths are similar since they are chasing each other. So each of the path is going to be completely congruent, right? So it's symmetry. Completely symmetrical diagram. You don't have to force it. You don't have to reflect anything or something. It's symmetry at the first sight. So let me show you the diagram, the actual one. Here we have. Now, the first thing, the beautiful thing about symmetry that you're supposed to notice here, the first insight that you should take here is the orientation, the configuration in the beginning. In the beginning is preserved. What does this mean? We had four bugs, right? The orientation between them, like they were arranged in form of a square, right? They were the vertices of a square. So throughout this whole journey, at any point t, at any time t, so let's say they reached here, they will always form a square. That's the beautiful thing about symmetry. No matter where they reach, the path will be something like this, right? The final path before the crash, right? So at any instance in this journey, if you take the positions of the bugs, they will be what? The vertices of some square. So the initial orientation would be preserved. This is the first thing that you're supposed to make. Now, the second thing is the center of the square. Center of the square. Center of the first square, the bigger one. This, it will remain the same for all the squares that are getting made. Like that, like throughout the whole journey, there would be like infinite squares. Yes. So the centers of all those squares would be same. Because why? Because they are symmetrical towards the same thing. Third thing that you're supposed to notice here is the line joining the center to the bugs always makes 45-degree angle with the direction of velocity of the bugs. Now what is this? This is the line that I'm talking about. In the beginning, since it was 45-degree angle with the direction of the velocity, at any instant it will remain, it will be preserved. Everything in symmetry is preserved. So at any instant it's going to be 45 degrees. Yes. Now coming to the fourth thing that you're supposed to notice. This line is very important. So as the bugs are like approaching the center, they're about to crash. This line is also like depleting, it's depreciating, it's getting vanished. So the moment they will crash, this line will vanish. We're supposed to find how long will it take for the bugs to crash. Instead of doing that, we can also do, like what we can also think is, how long will it take for this line to vanish? How long will it take for this to depreciate? It's corresponding. Both those things are corresponding. It will take the same amount of time, right? The moment they will crash, exactly the moment that this line will vanish, right? So instead of the bugs, we are now focusing on that line. All right. So we have had this line. What's the length of this line? This is basically half of the diagonal of the square. The diagonal of the square, it's a unit square, so that's root 2. This is going to be 1 by root 2. Right? So this is the distance that is supposed to be depleted. We'll need to find with what speed is the line depleting, in order to find how long will it take for it to vanish. This is the distance basically. Now, if you focus at any instant, as I told you, the angle here would be 45 degrees. The speed provided for the bugs is what? 1 unit per minute or whatever. One is the important thing here. So now I'm just going to break the speeds into its components if you've studied a bit of physics. So this component is going to be 1 cos 45. What is this? this is the speed by which the line is depleting. This is the speed towards the line, right? Even if you consider this position, it's 1. So this is what 1 cos 45, right? So this is the speed by which the line is depleting, 1 cos 45 degree. What's the distance? 1 by root 2. What is this? This is also 1 by root 2. We'll divide it distance by speed in order to get the time. That's 1 units. 1 minutes, whatever is provided in the problem. I hope this is clear. So this was the problem. We made some other correspondence. Instead of the bugs, we tried to find, like, focus on something that was easier to do, the line, a better distance, right? Alright, so the third thing that we're going to do today is transformation. You don't have to worry about this beautiful handwriting, I know. You'll be getting like notes, proper notes, handwritten notes, of course, uh, along with practice sheets for all those lectures that have already happened and for all those which are about to come as well. So you don't need to worry about that. All you need to worry is note down the problems that I give you in the class. So you won't get that in the notes. The practice sheets that you'll get, those will have different problems. So note down the problems that you're getting, nothing more than that. So yes, transformation. So this idea comes from like very old times, ancient. Like one of the most elegant proofs of the Pythagoras theorem was given using these techniques, and it was given by the Indians. It comes from ancient India. It's an extremely elegant proofs. Like the most, like, this theorem has hundreds of proofs, and this is the most elegant one. So just to demonstrate how transformation works, let me just show you that proof. I'm sure you know the theorem. Consider this to be a right angle triangle. This is A, this is B, and this is C. So the theorem says a square plus b square gives c square, right? Now, this is the algebraical form. This is the equation. So I'm just going to write a geometrical interpretation of this equation. For a square, I'm going to make a square of side A. You need to focus here on this diagram instead of this mess. For a square, we have a square of side S. For b square, I have a square of side B. Where is S? Side A. Okay. Yeah, so this is a bigger square that we'll be getting. Since this is B, this is also going to be B. This is A, this is B, A, B. So this, the square, the side of this square is going to be A plus B. A plus B. Sweet. Now, I've got this. I'm getting these two extra areas, right? Apart from A square plus B square. Now I'm going to divide these areas. These are the diagonals. If you see, this is A, this is B, right? So this is also B. This thing is going to be C. Why? Because that's the triangle that we have taken in the beginning, right? Similarly, this is also going to be C. So this square, if I try to write the area of this square, the area would be a square plus b square plus 4 extra triangles. Yes? Now, I have changed the orientation of those 4 triangles. Can I change? Can I do that? What I'll have to focus on? The length and the area is preserved throughout the whole procedure. I can do anything following this. Yes? So this is A, this is B, this is A, this is B, this is A, this is B, A and B. The side of the square is still A plus B, so it's the same square, the area is preserved, no difference. So it's same. I've changed the orientation only. Now if I write the area of the square, since this is A, this is B, this is going to be C, same for this, and same for this. We've got a small square as well, right? Now if I try to write the area of the square, I'm going to have C square plus the area of 4 extra triangles, right? Since these two are the same squares, this is going to be equal. This would get cancelled and we'll have a square plus b square equals c square. How beautiful is this? This is how transformation works. So this is the most beautiful proofs of the Pythagoras theorem that comes from ancient India. Anyways, so this is how the transformation thing works. Now let me just show you that thing, the technique on an area problem. So this was again a problem given to me by the same student. we are supposed to find the fraction of the square that is shaded. For that, we'll need to find the area of the shaded portion, right? Now remember the first session of lengths and areas. I told you to spot triangles with the same height. Same height. Can you spot? Can you do that here? If you try to notice these two triangles, this one and this one, let me. Okay, yes, this triangle and this triangle. Yes, they share the same height. This one, this is the height that they share. And since they have the same base as well, it's provided in the problem that these four parts are equal. So the areas are going to be equal. These two areas, this and this. Yes. So if the areas are equal, can I just like replace this one, this empty portion with this? I don't care what shape. What shape is this? Since the areas are equal, I'm just gonna assume that this is the empty area and this is the shaded one. Right? Would that make any difference to my answer? If I just make this shaded and do this, like make this empty? No difference, right? Since the areas are equal, same thing I'm gonna do here as well. So I'm basically gonna transform this here. Okay, so I'm not transforming yet, I'm just telling you. Okay, so this diagram will become something of this sort. This is the square that we had, this, right? This is also joined, and we have a diagonal, right? So instead of this, I'm shading this one. So this is the complete shaded area that we have. We have a better one than this. This was a weird diagram. We have a much more defined one, right? Now what else? These are the two empty areas. I'm gonna join them. Just transforming. I'm gonna join them. We got to here from here. Now I'm gonna just join them. So I'll get this. This is the beginning. So I'll bring this up. I'll get something of this sort, and this will be the shaded area. See how easy of a diagram. And this is what we have got now. This is all we have to do. So if you're able to find the lengths, these two lengths, which is easy to find from this problem, you'll be able to find what portion of the whole thing is shaded. So that is how easy transformation makes problems, area problems. Now, the actual like difficult problems that you'll be getting using transformations is this. Like they appear like if you scroll through the old Putnam PYQs and a lot of CMI problems, like in 2025, CMI asked one of the problems based on these. So these are the types of problems that include trigonometry. For now, I'm just going to give you a glimpse into this, the use of trigonometry. I'll of course explain. And the Euler's form of complex numbers. This one wouldn't use this, the complex number one. So this will only use trigonometry. Anyways, this is the problem. Before we get to the problem, one thing that I want you to understand. Consider this like there's a circle and there's a chord. We are interested in finding the length of the chord, right? This is the center. We're joining. These are going to be the radii. We're dropping a perpendicular. This angle is going to be equal. These two are going to be equal. Why? Because these two triangles, this and this, are congruent by what? By RHS. So by CPCT, those two angles are equal. Now in this triangle, if you notice, can I say that BC by OC is sine theta? OC is basically R, so BC is going to be R sine theta. Same goes for this as well. So this is also going to be R sine theta. Like it's easy to know, like if you know that perpendicular from the center bisects the chords, right? So the whole length of the chord is going to be 2R sine theta. Perfect. Now, so in order to find the length, we need this angle and the radius of the circle, right? Now, one more thing. This was the first thing. Second, with the regular polygons, if I wish to find the sides of the length of the sides of a regular polygon, so let's say I have a circle. I'll draw a circle immediately if I have a regular polygon. So these are the sides. Let's say this is a regular polygon. All right. So these are essentially what? Acting as the chord of the circle, right? So I have to basically find the length of the chords, these chords. What do I need? The angle. These chords must be subtending some sort of angle at the center of the circle. These angles, since the sides are equal to a regular polygon, these angles are also going to be equal. How many of these are the number of sides? Let's say, okay, so there's 1, 2, 3, 4, 5, 6, 7, 7 sides. So 7 equal angles. The complete angle is 2 pi. So one individual is going to be 2 pi by 7, right? So if I just take one part and zoom in, this part. So I have the previous situation. This angle is 2 pi by 7. This whole thing is 2 pi by 7. So if I drop the perpendicular, I'll have pi by 7 and pi by 7, right? This thing is going to be r sine pi by 7. And this is also r sine pi by 7. So the side of that polygon would be 2r sine pi by 7. Yes? Now coming to this problem. The moment you see a regular polygon, this is the insight that you got. The moment you see a regular polygon, you'll be drawing a circle, you'll be thinking of trigonometry, you'll be thinking of finding the angle that the sides are subtending at the center of that circle. Alright, so this is the diagram. Okay. We're supposed to prove that a1a3 square plus a3a7 square plus a1a7 square equals 7r square as the radius of the circle. These are also the chords, if you see, right? We have to basically find the lengths of the chords at first. This chord, what do we need? The angle it is subtending at the center. We know that this angle, this thing, is going to be how much? 2 pi by the number of sides. How many sides? 14 sides. That is going to be pi by 7. So since this is pi by 7, this is also going to be pi by 7. So the angle subtended by a1, a3 is going to be 2 pi by 7. Yes? Now this is not theta. This is the mistake people do. The length of this is going to be 2r sine theta, I know. But this is not theta. You'll have to divide it using the perpendicular. Notice this whole thing is 2 pi by 7. Theta is half of 2 pi by 7. So it's going to be 2r sine pi by 7 actually. This is what? This is the length of a1, a3. Similarly, for a1, a7, if you see, a1, a7, how many? 1, 2, 3, 4, 5, 6. 6 of them. So the angle it is subtending is 6 pi by what? 7, right? And the length is going to be 2r sine 3 pi by 7, right? For a3, a7, it's subtending 4 pi by 7 of an angle. The length is going to be 2r sine 2 pi by 7. So we are essentially supposed to prove that 4r square into sine square pi by 7 plus sine square 2 pi by 7 plus sine square 3 pi by 7 equals to what? 7r square. Now there are multiple identities in order to do this. Like you can use manipulations. We are only left with there's no geometry anymore. There's nothing about Euclidean geometry here anymore. Whatever it was still here only. Alright. So here you have to use trigonometric manipulation that we'll be doing in like future problem sets and stuff. So yeah, you'll find that this is 7 by 4. This comes out to be 4 and 4 would get cancelled. So 7r square would be what you'll be left with. Anyways. Alright, so the fourth thing that we're going to do today is locus. I've saved the best for the last. We're not actually discussing locus here. Um, we'll be using this in areas and stuff. And we'll be using the areas to prove some very unusual things, unusual problems, like collinearity. One of the things. Now, collinearity is not unusual. Proving collinearity using areas or using locus is. So, before I get into this topic, let me mention this very explicitly. This is going to be a bit longer, and this will require most of your attention throughout the session. So, you'll have to stick till the end. You may feel like, what the hell are we doing? You may feel lost, directionless and stuff. But stick with me till the end, and every piece will fall into place. All right. So locus we're doing. Formally, if I talk about locus, it's basically a set of points, and a set of point would make what? A path, right? A set of points which are constrained. All these points, each of these points are constrained by a fixed geometrical condition. What does this mean? Okay, let me demonstrate this to you. Let's say I have two lines, L1 and L2. All right. I want to find the locus of a point M such that M is equidistant from L1 and L2. Now, it's not very difficult to understand that you'll find a lot of such points, right, which are equidistant. You can find it here as well. You'll find infinite point. I can go out of the screen as well and find one point. You can find it here as well, right? So it will be a lot of points, So you don't have to be specific. You don't have to be limited to M just because the problem says. The problem would be stated like this only. It says to find the locus of a point M. This does not mean you have to stay limited with one point M. This is acting like a spokesperson for all those points. This is a denotion for all those points that are following this fixed geometrical condition that I was talking about in this definition. This is the geometrical condition, being equidistant from L1 and L2. So these are multiple points, infinite of them. I'll join them. I can join them, right? I'll get what? A path. This path is what we are calling as locus. So I'll say this is the locus of the point. Now in problems regarding locus, you don't like show this. You see, this is locus. You don't do that. You give an equation of the line, or maybe if it's a special line, like in this case, it's the angle bisector of this angle. So yeah, you do that. Now one more thing, actually the same thing that I want to tell, that it may sound trivial, but it's important. If I say, if I consider a point A on L1 and B on L2, and there's some point P such that PA equals PB, all right? And let's say I have C on L1, D on L2, and once again, there's some point Q such that QC equals QD. What conclusion can I make from here? I'll say that P and Q, both of these lie on the same locus as M. I'm saying the same thing, same exact thing. Let me just mark it here. C, D, and Q, A, B, and P. Yes, same locus, same locus. Now this may sound very trivial to you, but when you'll feel lost at the end in the problems, this will help you. All right, so I'll be referring this as the green point. Anyways, this was locus. The problem that we have to discuss today. Let me just get back to red at first. Yes, the problem that we are discussing today is we have to find the locus of a point M for a triangle ABC such that area MAB equals area MAC. All right, so I have a triangle. I've got a triangle ABC. I'm supposed to find the path of all those points, right? There are going to be multiple points such that this happens. Let me just make M here, consider M here. So MAB, MAC. This is the area we're talking about. Now this is where you have to like let your imagination flow. All right. So there are going to be multiple points. We don't know. Like I put M inside of the triangle. We're not sure of that, right? M can be on the edge of the triangle as well. Edge of the triangle. M can be outside the triangle. M can be anywhere in space. All we have to follow is this condition. There's no condition provided for M, right? M can be inside as well. These are the three cases that we'll be studying. All right. So first of all, let me do it for M being on the edge. That's going to be the first case. Let me first like drag these diagrams down. We don't need these as of now. Sweet. All right. So these are the three cases. So the first case we are doing is M on the edge. What does that mean? We have a triangle ABC. We have some M on the edge of BC, let's say. It can be on this as well. That, like, without any loss of generality, we're considering it on here. We're supposed to follow the condition that MAB equals MAC, the area, right? So MAB equals MAC, these two areas. Now, you may be able to notice that they share the same height. So they'll have the same area. For them to have the same area, their bases needs to be equal. So MB should be equal to MC, right? What does that mean? That means that M is what? The mid of BC. What does that mean? That means AM is what? The median of the triangle. Sweet. Now, second case. M is inside this diagram. M is inside. Let me change the color. All right. So M is inside the triangle. Now we can use this diagram actually. So M is inside the triangle. Let me decrease the size as well. Sweet. So M is lying inside. We're supposed to follow again the same condition. MAB equals MAC, right? Sweet. So if you see, those two areas are sharing this same base, AM, right? Equal base, actually the same base. So in order for them to have the same area, they need to have what? The same height as well. This is the height for triangle ABM, and this is the height for triangle ACM. I want you to focus on these two triangles. Now these two heights are like perpendiculars to the same line, which is this. So they must be what? Parallel, right? So these two angles are going to be equal. Why? Alternate interior angles. These two are also going to be equal. Vertically opposite angles. This is already 90. So by triple A, these two triangles are what? Similar. Now in order to have the same area, what's the necessary condition? The heights need to be what? Equal. So for two similar triangles, if you remember when I was talking about similarity, um, I gave you a corollary that if the coefficient, like if two triangles are similar and one of the corresponding pairs of sides become equal, the coefficient of similarity becomes 1, and hence the triangles become congruent instead. So these need to be equal, and hence these two have to be congruent, and once they get congruent, we'll have what? BD to be equal to DC. BD to be equal to DC. What does that mean? D is once again the mid of what? BC. That means AD is the median of BC. Right? Perfect. All right. Now, for outside cases, for the outside one, okay, let me just move this diagram. Okay. So for the outside one, case 3, the outside. For this case, we'll have two subcases because two things are possible. Remember, for the first case and the second case, all we have got is the points need to be on the median of the triangle. So we're concluding this to be the locus for now, for the first and the second case. Yes? All right. For the outside case, there are two things that are possible. M can be here as well, like A, B, C. So I'll have MAB to be equal to MAC. So AM is the same base. We need to have the same height, right, of these two triangles. And once again, if you notice a bit, we'll end up getting that M should lie on the extension of the median. It's understandable from this diagram as well, like M is somewhere here or on the extension. If you keep extending, like, and considering the area, right? So that will be the case. Anyways, so this was the subcase 1 when M is here. Now one more thing is possible. That is explained in the second diagram. M can be here as well. This is the triangle. This is the triangle. Earlier we were considering for the outside case M to be here. M can be here as well, right? Also, M can be here as well. On the extension of the median, it can be anywhere. But one other case we are getting, that if M is here, what condition do we need to follow? MAB equals MAC, right? So MAB equals MAC. These two share the same base, that is AM. They need to lie, these two triangles need to lie in the same parallel in order to be what? In order to have the same area. That means AM needs to be parallel to BC, right? Perfect. So three cases we discussed. First one, M on the edge. On the edge. What did we conclude? It's on the median. Second, M in the interior. It's still on the median. On the median. And not only in the interior part of the median, on the extension as well. So this becomes the first case of the first sub case of the third problem as well. So extension of the median, right? For the third, when M is outside, we concluded it's either on the extension of the median or AM is parallel to BC. M lies at a position such that AM becomes parallel to BC. I hope this is clear. Now, what do we conclude from here? Let me call this as lemma 1. Just stick with all this, whatever is going on, just stick with it. If you're able to understand, that's great. Stick with it. Lemma 1, let me call this. Okay. So we are saying locus of a point M such that MAB equals MAC for a triangle ABC. Like for this to happen, there are first of all two conditions possible. Like this is only possible in two conditions. What are the conditions? AM, okay, let me say M lies on the median, or AM is parallel to BC, right? In all the three cases, the first two cases we concluded the median thing. For the third, we got this new thing. So in all, we have two conditions for this to happen, right? Yeah. So the locus would be the median here, and this one more condition. Okay, so note this down. Okay, don't note this down. You'll be getting it in the notes anyway. Now, we are upgrading ourselves a bit. We had this, these two areas. We are making them equal, A, B, C. Now, when I make it in the interior, don't get limited to it. You should be able to think of all these points lying on this locus. All these points lying on this locus. All right? Okay. So, yeah. Now, what we are going to do is, we're going to translate AB to A dash B and AC to A double dash C. What exactly does that mean? We're going to do some sort of this sort of stuff. Okay, M still stays there. We basically like opened it sort of A dash B, A double dash C. This triangle we opened it from here kind of thing. Alright, so A dash, A double dash. We are still interested in finding the same thing. We're interested in finding the locus. Let me change the color. Finding the locus of M such that M A dash B equals M A double dash C. Is that clear? Sweet. So this is what I'm talking about. Okay, these two areas. All right, now this also looks like, if you, I'm sure you're able to notice that this looks like what, a quadrilateral, right? So let me just rephrase the problem. Let me just say, find the locus, of a point M, in the interior of a quadrilateral ABCD such that MAB equals MCD. Yes. So I'm having this quadrilateral. We also provided that AB is not parallel to CD. All right. Otherwise, it would be too easy. We're not given any such triangle. We have to like comment on a normal one. So basically, we are moving from a triangle to a quadrilateral. All right. So yeah, we have A, B, C, D. Perfect. We've got M in the interior. Yes, in the interior. So MAB and MCD. Okay, this is a single point. So these are the two areas that we are supposed to talk about. This is the geometrical condition. All right. So what we'll do is we'll extend AB and CD. Since they're not parallel, they will what? They will intersect at, let's say, T. This is what is being done here in this diagram. If you see, we have this quadrilateral ABCD. Yes, and we extended AB and CD such that they're intersecting at T. What else are we doing? We're marking X and Y such that TX equals AB, such that TX equals AB. These two lengths are equal, and TY equals CD. TY equals CD. In other words, this is called as, we are translating AB to TX and CD to TY. We are doing what? Translating. We'll be doing this. Don't worry about that. So this is what it means. All right, we have chosen X and Y such that TX equals AB and TY equals CD. Why are we doing this? Since we are comfortable with a triangle, right? We have already dealt with a triangle in a lot of detail, so we know how to deal with them. So we are basically converting the quadrilateral problem into a triangle, if that's clear. All right. So let me just drag this diagram down. Okay. Sweet. Wow. Okay, we'll be doing that problem later. Ignore that for now. All right. So we have this. We did that. We translated them and they were intersecting at T. Perfect. Now, the geometrical condition that we were provided with was MAB should be equal to MCD. These two triangles, right? If you notice, then MAB is equal to MTX, the area I'm talking about. Why? Since TX is equal to AB, and these two, this is the triangle I'm talking about, MTX. Since these two triangles share the same height, and since their bases are also equal, the areas are going to be equal. Yes. Similarly, MCD is equal to MTY. MTY. Yes, are you able to focus? MTY and MCD. See, they share the same height, and since CD is equals to TY, that's how we have chosen Y. So we can say this as well. Now, can I say that maintaining this condition, this geometrical constraint, is equivalent to maintaining this? Since this is equal to this, I can write this in place of this, and I can write this in place of this, right? So I'll say, instead of saying this, I'll consider the geometrical condition to be MTX equals to MTY. How sweet. Now, if you're able to notice from lemma 1, this is exactly that. This is the first case, first subcase of case 3. Case 3 was what? M outside the triangle. I'll tell you what triangle I'm talking about. I hope you have already noticed that, but if you haven't, it's okay. First subcase was on the extension of the median. Of the median. The triangle I'm talking about here is triangle TXY. Triangle TXY. Yes. What do we have to prove? MTX equals to MTY. It's exactly like saying MAB equals to okay, MAB equals to MAC for triangle ABC. What did we do? It always lied on the, if it lies below, like the point, so it was where? On the extension of the median. So M should be where? On the extension of the median of triangle TX. So let me just erase the mess. Yes. So this is the triangle that I'm talking about. And M from lemma 1 should be on the extension of the median of triangle TXY. So the locus will say, the solution to our problem will say that ABM, the locus of point M, such that ABM equals CDM is the portion of the median of triangle TXY which lies inside the quadrilateral ABCD. I hope this is clear. And of course we know what is TXY. We'll have to do like tell, like in the solution, like T is the intersection of AB and CD, and X and Y are like points taken such that Tx equals AB and Ty equals CD. I hope this is clear. You may want to repeat this and stuff, whatever you want to do. Anyways, so let me erase this and get to some problems. So this was basically lemma 2. Let me write this as lemma 2. This is not really a lemma, but just so you're able to connect this and remember this well and later try to use it. I suggest you to prove these, whatever, these lemma 1 and lemma 2 on your own. Think of every argument on your own. That would be better. Lemma 2. That was the lemma 2 that I just wrote here. So the locus of a point M inside a quadrilateral, it's basically a trapezium, or we call that a trapezoid as well, ABCD, such that area MAB equals area MCD is the portion. We have to basically comment on ABCD, right? So it will be this part of the median. So we're not really focusing on this. In the original problem, we're provided with the quadrilateral only. So we'll comment on that only. That is why I'm writing is the portion of the median of triangle TXY, which lies the portion which lies inside quadrilateral ABCD, where T is the intersection point of AB and CD, and Tx equals AB and Ty equals CD. I hope that is clear. Try to prove this on your own. Sweet. Now I'll be erasing this actually. We'll be doing the problem. and I'll be deleting the diagram as well, so I hope you have. Okay, sweet. So this is a problem that we have. It's an easy one. If you followed the first part, it's an easy problem. The lemma one, based on that, we're supposed to find the locus of a point M and of points C, points M in plane of triangle ABC such that ABM equals 2 area of ACM. So we have a triangle ABC. We're supposed the geometrical condition here is ABC should be equal to, sorry, ABM equals 2 ACM, right? So let's say M is here somewhere. So this is ABM and this is MAC. What are we comfortable with? We're comfortable with a situation like this. We don't know how to like deal with if some sort of coefficient is written here, right? So we'll get back. We'll try to, you know, take this back to the condition that we're comfortable with. How do we do that? We are saying twice of ACM. This is ACM. This is ACM, right? Twice of this would be, let me extend AC to some point, let's say D, such that AC equals CD, right? And I'll connect M to D. Okay, that is not very straight, but I hope you understand that. Okay, so I'll connect M to D. All right. Now, if you focus on triangle AMC and triangle MCD, these are the two triangles I'm talking about, AMC and MCD and MC. All right. They share the same height, right? And the equal base. We have extended AC such that AC equals CD, right? Equal base, same height, the areas are going to be equal. Yes. So instead of this triangle, can I consider, let me change the color, can I consider this triangle? And M stays there only. What I'm saying is, we had this sort of thing. M was here, right? We extended this, we joined this, we extended this such that this was equal to this. And now, this is what we want. MAB to be equal to AMD. What is AMD? AMD is basically this whole area, whole area, and this whole area is basically twice of AMC. This is what we had to prove. So from here, we got to a condition that we are familiar with. So MAB equals AMD. That is sweet, right? So we'll join instead this part and we'll deal with this bigger triangle. I hope you're able to deal with it now. Like it's easy to comment from lemma 1 now, right? We know it that M would lie on the median of which triangle? Not ABC, ABD. I hope this is clear. Now a similar problem on a quadrilateral. So I hope you try. Alright, so this is the problem. This is a bit better one. Alright, so this is the collinearity problem that I was talking about. We are provided with a trapezoid. As I told, this is a fancy name for trapezium. We are supposed to prove that the midpoints of the parallel sides, the points of intersection of the diagonals, and the point of intersection of the non-parallel sides, they all are collinear. So here we have the trapezium. The midpoints, we are calling them as P and R of the parallel sides. The intersection point of the diagonals is Q, and the intersection point of the non-parallel sides is S. So we are supposed to prove that P, Q, R, and S, they all are what? Collinear. So let's deal with one at a time. P. Can I say that area ABP equals area CDP? Let me highlight that. Area of ABP and area CDP. Let me actually draw that with a different color. ADP and CDP. Why? P being the midpoint makes the bases equal. And since AD is parallel to BC, so these two triangles lie in the same parallels, making their areas equal. What exactly is this? I hope you are able to connect it with lemma 2. Right? What did we have in lemma 2? We had some trapezium and we had a point inside such that these two areas were equal. Now remember, I told you, now remember the green property, the green point in the beginning that I told you. If I say, like here it was AB, C and D, I was saying MAB equals MCD, and the locus was what? The median of that extended triangle, right? This triangle, right? So now I'm saying that PAB equals PCD. Earlier it was MAB equals MCD. We have PAB equals PCD. What will I say? P also lies on the same locus. What locus? The median of what triangle? Of this triangle that I'll make. And what exactly is that triangle? We'll have to translate AB to some x, translate CD to some y, and this SXY is the triangle, the median of this triangle. P lies on that by the green property, by the green point and lemma 2. I hope that's clear. I hope you're able to connect. Now similarly, now let's come to R. We have dealt with P. Let's come to R. Alright. So if we talk about R, can I say RAB equals RCD, the area? Once again, similarly, let me use a different color, some ugly color. Okay. So RAB equals RCD. Yes, exactly like that, like we did here for P. Can I again say R also lies on the same median, same locus of triangle SXY, right? So since P and R lie on the same locus, they become collinear. Like, yes, P, S, and R become collinear. S, how did S come from? Like S is the point that is connecting the median, right? So S is like trivial. So P, S, and R become collinear. Now, if I prove somehow that Q also lies on the same median, same locus, then I can say Q is also like collinear with P, S, and R, right? What will I need to prove in order to say that Q lies on the same locus? I'll have to say that QAB equals QCD, the fixed geometrical condition. Is that correct? Okay, now let me erase this mess. Wow. Okay, so QAB equals QCD. This is what I need to prove. If you see, area of ABC equals area of DBC. Why? This triangle I'm talking about, these two triangles. Are their areas equal? Same base and between the same parallels, right? Can I write ABC as QAB plus QBC? Okay, let me just make it a bit clear for you. Can I write ABC, this whole thing, as ABQ plus QBC, right? And similarly, I will write DBC as QCD plus QBC. You see, QBC is the common area between those two triangles, right? I hope it's not getting like messy. So QBC and QBC gets cancelled. We have QAB equals QCD. That's what we wanted. So Q, P, R, and S are what? Collinear. Was that fun? This was the whole point. Like, try to prove lemma 1 on your own, lemma 2 on your own, everything on your own. Try to visualize locus, understand what a locus is. It's not about a single point, it's about the whole thing. Yes? And apart from that, solve these problems on your own. Try to think originally. You'll get more problems on these in the sheets, in the practice sheets that you'll be getting very soon, and the notes as well very soon. Today we did 4 things. Let me just give you a bit of recap. 4 things we did. What was the first thing? The carpet sliver. Second, symmetry. Third, transformation. And the fourth is this. So I hope this all become like you're clear with all these 4 things. We'll be moving ahead with our Euclidean geometry course now. From the next lecture, we'll be doing some theorems in triangle geometry, and also we'll be getting a bit of trigonometry and stuff, trigonometry, so that we can further study the centers of the triangle. All right. So I hope this session was enjoyable for you. So I hope to see you soon. Thank you.